Good morning, students. Welcome to your physics class. I hope you are doing good and are in good health. So let's start with our class. Good morning, students. In our today's class, we are going to start our new chapter, that is gravitation. So there are few general questions like why does Earth satellite revolve around the sun? Okay, and why does Earth revolves around the sun, or why do other planets revolve around the sun? Isn't it? And we know that there are millions of stars in our universe. So why there is no random collision between them? Isn't it? And why there is no random collision between all the planets, and um, like what is the difference between mass and weight, isn't it? So all these questions will be answered in this chapter. Okay, so let's begin with it. In the 16th century, there was a scientist named Johannes Kepler, and he had derived three laws which governs the motion of the planets. Okay, that means Kepler had given three laws regarding the planetary motion. Okay, but the scientist Kepler could not give the exact theory to explain the motion of the planets. Okay, so after Kepler, it was Newton who showed that the cause of planetary motion is the gravitational force that sun exert on them. Okay, that means the primary cause, the real cause of planetary motion was the gravitational force that sun exert on all the planets. Okay, so what Newton did, Newton made use of the Kepler's third law of motion. Okay, third law of planetary motion, and had proposed universal law of gravitation. So universal law of gravitation was proposed by Isaac Newton. Okay, universal law of gravitation says that every object in the universe attracts every other object with a force, with a force. Okay, and it will later give the value of that force. Okay, so with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. This is the statement of universal law of gravitation. Okay, this statement is saying, assume that there are two objects. Okay, this is my object A and this is my object B. Their masses may or may not differ. Okay, there are two objects with different masses. Okay, I'm assuming this as object A and I'm assuming this as object B. Okay, and this is the center of object A and this is the center of object B. Okay, so any two object in the universe will attract each other with a force, and that force is what? Gravitational force. Okay, and that force will be applicable, this force will be applicable, or this force is along the line joining the centers of two objects. Okay, this force will be what? This force, I'm assuming this as capital F. This is the force of attraction between any two objects placed in the universe, and the value of this force will be what? This force will be directly proportional to the product of their masses. Every object in the universe attract every other object with a force which is proportional to what? Product of their masses. So this force will be proportional to what? Product of their masses. I'm assuming that it has mass capital M and it has mass small m. I'm writing it as capital M and small m in order to show that both are the masses, okay, and but of different objects, okay. So I have represented one as capital M and another as small m. You can take another format also, like M1 and M2, okay. So I'm here taking capital M and small m as the masses of both the objects. So force of attraction will be directly proportional to what? The product of their masses. That means this, okay. Now the, and what else is said? And inversely proportional to the square of the distance between them. What is the square of the distance between them? First see what is the distance between them. I'm assuming that both are being placed d distance away, okay. Both have distance between them as d meter, okay, small d meter. So this is the distance between both the objects, and this distance will be calculated with respect to the centers, okay. So I am taking from the centers the distance between them, okay. So this force of attraction will be what? It will be inversely proportional. So first I have to write 1 divided by inversely proportional to the square of the distance between them. What is the distance between them? D. What is the square of the distance between them? D square, okay. I'm assuming this as my equation 1 and this as my equation number 2. Now combine both the equations, we'll get force is directly proportional to m into m, isn't it? It is the directly proportional, and the d square will be what? Inversely proportional. So I am taking it in the denominator, okay. So now remove this proportionality sign. It will be removed with proportionality constant, and this constant I'll be taking capital G, okay. So this is my expression for the value of the force of attraction between any two objects that are placed in the universe, okay. So this is the value of the gravitational force between them, okay. What is G? G is my proportionality constant, okay. So G is what? A proportionality constant. It is a special type of proportionality constant. It has another name, that is universal gravitation constant. Since it is a constant, so I am naming it as universal gravitation constant, okay. This is a proportionality constant that has been bought by removing the proportionality sign with equal to sign, okay. So this G is what? My proportionality constant, and this is a special type of proportionality constant. It has another name as universal gravitational constant, okay. Now let's study this proportionality constant in detail, okay. Now bring the value of the proportionality constant from this equation. We will get what? First rewrite it, G m into m divided by d square, okay. Now rewrite it, F into d square. I have brought this d square in the numerator. Okay, so here this will be left. Okay, now g will have value as f into d square divided by m into m. One more important thing, do not multiply this m into m as m square. Okay, because these two are not the same quantities. These two are different quantities of masses. Both are the masses of two different objects, not single masses. Okay, now in place of this you could have write what, m1 into m2. Okay, now this is the value of proportionality constant. This is the value of universal gravitational constant. Okay, and one more thing students, g has, and since g is a what, constant value, so g must be having a constant value, isn't it? So it has a value of 6.673 into 10 to the power minus 11. Okay, Newton meter square kg to the power minus 2. From where this unit has come? See here, what is the SI unit of force? Newton. So in the numerator I'll write Newton. Okay, now what is the SI unit of distance? Meter. Why? Because the small d is what, the distance between two objects, so it will have some value in meter. Okay, so I'm bringing it as m square. I'm writing it as m square. Okay, since it is the square of the distance, so square of the SI unit. Okay, in the denominator both are the quantities of what, they are the masses, so this will come in kg into kg, so it will be what, it will be kg square. Okay, so it will be what, Newton meter square. If I want to bring this in the numerator, so power their power will get inverse, so it will be what, here it will be what, kg kg to square. Okay, so here it will be what, kg to the power minus 2. Okay, this way we have got this, the SI unit of a universal gravitational constant, that is Newton meter square kg to the power minus 2. All right, this is the value of universal gravitational constant. Okay, now as we are seeing that this universal gravitational constant has a very small value. Okay, since it has a very small value, so gravitational forces are the weakest force in nature. This constant is showing us, universal gravitational constant is showing us the gravitational constant value. So since it is very small, so gravitational forces are weakest force. Now if you are asked to define g, then how will you define g? Since we know that g has this value, universal gravitational constant will have this expression, so this expression will reduce in, since we know that d is what, distance between two objects. So if the distance between two objects is what, 1 meter, and if both the masses, both the point masses m and small m is equal to 1 kg. Okay, if d will be 1 and m and small m will also be 1, then what will happen? Then g will reduce in what, force, and force is what, the gravitational force. Okay, so universal gravitational constant will be equal to gravitational force when the distance between the two objects is 1 meter and when their masses is of 1 kg. Okay, G will be equal to F when D, M and M is 1. If the value of the d square divided by m into m will be equal to 1, then G will get equal to F. So can I say that universal gravitational constant will be equal to gravitational force when the two objects will be placed 1 meter apart and when the both object will have masses as 1 kg. Okay, so let's define G. G is what? The universal gravitational constant, isn't it? So the universal gravitational constant is the force of attraction between the 2 point masses, okay, of 1 kg each and are kept 1 meter apart. Okay, so the universal gravitational constant is the force of attraction. Universal gravitational constant is the force of attraction between 2 point masses of how much kg? Of 1 kg each, and they must be kept in at 1 meter apart. Okay, so 1 kg each kept at a distance of 1 meter apart. Okay, so my universal gravitational constant will be equal to gravitational force of attraction when the 2 point masses are of 1 kg each and if they are placed 1 meter apart from each other. Okay, this is the definition of G. Okay, and we know that it has value of G is equal to 6.673 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Okay, universal gravitational constant has this value. Okay.